Hello, everyone. So first of all, I want to thank the organizer for the invitation and for making this conference possible. So I'm going to talk about the scaling limit of random planar math with large faces. And this is a joint work with Nicolas Curien and Grégory Mirmont. So it is not yet on archive, but I hope it will be pretty soon available for everyone to read. And OK, so let's start. So I'm going to give a very large overview. I'm not going to say anything precise. So if you have any question, just ask now or after. OK, and I'm going to start with some context and general facts about planar maps and their scaling limits. And a lot of things have already appeared in the other talks. So I'm going to be a little fast maybe here. So for me, in this talk, a planar map is just a gluing of polygons in order to obtain a topological sphere. And here we have an example where I have just squares to obtain a sphere. And all the planar maps I'm going to consider are bipartite, meaning that all the faces have even perimeter. This is not a philosophical constraint, but a technical one, and is to make our life easier in the proof. But everything I'm going to say should work for more general maps, but we only work with this bipartite constraint. And as always, we consider these objects up to our homomorphism of the sphere, and we always distinguish a half edge, and the root is going to be the starting point of the distinguished half edge. Okay? And just a little precision, I'm not going to consider matter in this model. So noising model, no loops model. So I'm not going to talk about it, even if what I'm going to say is more or less connected to that. We saw something in that direction in Marie's talk, but here I won't have time to precise it. So the reason why I'm interested in planar maps, or one of the reasons, is because there are models of compact metric spaces. So if you take a planar map, the set of vertices with the graph distance and the root, you have a pointed metric space. And as the set of planar maps is discrete, we can define nice and good probability measures on this space. And the ones I'm going to consider are Boltzmann measures that we have already seen. And the idea is just really to generalize the Galton-Watson trees and to have a good measure in a product form. And to do that, we fix some weight sequence, Q, of non-negative numbers. And we introduce the measure, the following measure. So the mass of M is just the product over the faces of Q of the half perimeter of the face. Okay, so of course this is not a probability measure. So we need some constraints on the weight sequence to be able to do probabilities. And as we are going to consider scaling limit, we also need criticality constraints. But I'm not going to give here the exact assumption that we need. Okay, they are explicit in terms of Q, but in this talk, let's keep the things like this. And one of the fundamental results of the theory is that we have a scaling limit. So and the first result in that direction was obtained by Le Gall and Mirmont in an independent way. And they show that if you take a uniform quadrangulation with n vertices, then if you rescale the distances by n to the 1/3, you converge to some continuous random metric space called the Brownian sphere. And here you have a simulation. So just to explain the notation, S is just the set of points of the Brownian sphere, delta is the distance on the Brownian sphere, and rho star is just a root. Okay. And as it has been already said in this conference, the Brownian sphere is a universal object, meaning that a lot of models converge to the Brownian sphere. And morally, if your model does not have large faces, then you should converge to the Brownian sphere. I want also to mention that there is another point of view to this theory, it's the Liouville quantum gravity point of view, which is very rich and has been developed a lot in recent years, but I'm not going to talk about it today. Okay. And so this was all I wanted to say about the general context of planar maps. And now I'm going to consider other models of maps which have large faces, that are going to converge to a new class of canonical continuous and random surfaces. And to give a more or less precise definition, I'm going to consider stable maps, which are Boltzmann maps, with this kind of weight sequence. So here we have some asymptotic behavior. The exact behavior for this talk is not so important. The important thing is that we have exponential term, which is not very important, and a polynomial decay in alpha plus 1/2, and alpha is between 1 and 2. And the idea is that in this regime, the perimeter of a typical phase is in the domain of attraction of a alpha stable law. So things are going to be different, and in fact, the phases are going to appear in the limit, which is not the case for the Brownian sphere that has the topology of the sphere. So here are some simulations. So for different kind of alpha, of large stable maps. So we see that when alpha is close to 2, we have something that looks like the Brownian sphere, but with a few large phases, but okay. It looks like the Brownian sphere more or less. And when alpha becomes smaller and smaller, the phases become bigger and bigger. And in fact, we have a phase transition when alpha is equal to 3/2, and I will explain later why. Okay, but this is the picture to keep in mind. And I want also to mention that this kind of maps have already been studied a lot. And in particular, Le Gall and Mermont proved more than 10 years ago that we have a tightness result. So if you consider this kind of model, you can take a subsequence such that you have convergence to some continuous random space. And you can say, and they say things about this space. For example, they prove that the Osborne dimension is always 2 alpha. So now I can state our main theorem, and the idea is just to prove that we have convergence. So more precisely, if we take Mn a stable map condition to have n vertices, then we have the following convergence from Gromov-Hausdorff topology. So if we rescale the distance by n to the 1 to alpha, the distance, then we converge to some continuous random space that we call the alpha stable carpet if alpha is bigger than 3/2, and the alpha stable gasket if alpha is smaller than 3/2. Okay, and here again, S alpha is the set of points, delta alpha is a measure, a metric on this space, and rho star is just a root. And here I have added a constant CQ because the scaling limit in some sense depends on the model that you are considering, but just for this constant here, that depends in an explicit manner, but I'm not going to give here the definition, and I will take just C equals 1 because it doesn't change anything, it only multiplies distances. Okay. So this is in some sense an abstract result, and what I want to explain in the rest of this talk is that in fact the scaling limit, which depend on alpha, is something very concrete, and we can study it directly in the continuous, and we know a lot of things about it. And here are, I have enumerated some of the properties that we have. Some of them depends on alpha and others not. So for example, for all alpha, the phases appears at the limit. So the large phases converge to large phases in the continuous. So you don't have any longer the topology of the sphere. But we have that all the phases have Osborne dimension 2. And that's a good news if you want, I don't know, to fill the phases with Brownian disk or to glue together. So boundaries is a good thing to have. And even if the topology is not that of the sphere, we show that the scaling limit that we obtain are planar, meaning that we can embed the scaling limit in a continuous and injective way on the sphere. And that's very important, in fact, for our proof, because we can use Jordan theorem and this kind of stuff. Okay. And if alpha is between 3/2 and 2, then the phases are not very large, and the topology is just simple loops. So you have injective cycles. And in that particular case, we are able to understand pretty well the topology, and the topology is that of the Sierpinski carpet. So this is just a universal topological curve, and it does not depend on alpha, and it's deterministic. And because, of course, our convergence theorem characterizes the topology, but another thing is to understand it. And when alpha is smaller than 3/2, things are more complicated, and phases are so large that they become self and mutually intersecting, and we don't know really if the topology depends on alpha or if it's random or not. We have some ideas of how to tackle this question, but we don't have a proof at all, and we won't prove it in this work. Okay. And now, what I want to do is to explain you who is S alpha and how we can construct it using canonical stochastic processes, okay, that we can really understand and that they have some geometrical meaning. And the idea, as always, is to come back to the script and look at what is happening. And as on almost every talk, we are going to consider encoding of planar maps using label trees. So I'm going to use here the Boutier-Di-Francesco-Guiter encoding, and this is a bijection between bipartite planar maps and this kind of trees. So the bijection is more general, but I'm just staying in this particular case. So we have two kinds of vertices, white and black, and the white vertices have labels. The root have label 0. Okay, and we have some constraint of the label that I will explain later. And each black vertex is connected only to white vertex and vice versa. Okay. And what I'm going to do is just to consider a slightly modification of this object, which is, okay, it doesn't change anything, but it changes a lot of things when you represent the object in your head. So the only thing I'm going to do is for every black vertex, I'm going to consider all the white vertices around it, and I'm going to follow the orientation of the plane. And the only thing I'm going to do is really is just to connect every white vertex with his neighbor. So I'm going just to do that. And I will obtain, like this, a loop. Okay, that's not good at all. Up. Okay. And I don't have and then I'm going to remove all the connection inside the loop. Well, that's not. Okay. So I'm just going to do that. Okay, yes. And so I obtain this loop tree. And now the constraints on the labels are very easy. Is that you follow a loop, you can only decrease by -1. When you turn around, you can only decrease by -1. And then that's the only constraint. And this doesn't change anything because you can recover the label tree. But what happens is that the loops will have an interpretation at the scaling limit. The loops are going to become the phases. And now I can just explain what is the Boutier-Di-Francesco encoding for this kind of object. So as usual, we add a new vertex with label, the minimal label -1, and then we perform the Scheffer type construction. So for every white vertex, we follow the contour, for every corner, but we follow the contour until we find a vertex with label smaller than the previous one, and we draw a red edge between them. So here, for example, 0 is connected to -1, and 4 to 3, and so on. And when we remove the loops, we obtain a bipartite map, and this is a bijection. And what happened? Okay, that's a very useful bijection, and the idea now is really to try to encode these two objects with random paths. Because, okay, here is a nice thing, but what we know how to do is to take a scaling limit of processes. Okay? And we are going to use two processes, and that's really useful to have really two kind of things. One thing is going to encode the loop tree structure, so the geometric structure of your tree of loops, and something that is just looking at the labels. So to encode the loop tree structure, we use the Lukasiewicz path. So you can think about it, just you follow the loop tree, and when you see a loop, you make a jump of size, the size of the loop -1. If it's not the loop, you take -1. And the label process is just more or less the same thing. You follow the contour of your loop tree, and you look at the labels that you see. And of course, you can recover the loop tree with the Lukasiewicz path, and the labels with the label path. So you can recover the discrete structure here. And Le Gall and Armand proved more than 10 years ago that these two processes, when you take stable maps, converge to stochastic processes. So the Lukasiewicz path is going to converge to alpha stable Levy excursion. So you will have jumps at the limit. And the label process converges to some continuous and complicated process, a stochastic process. And I'm not going to give here the exact definition that they gave, because we will see that it can be, there is a nice way to think about it. Okay, but the important thing is that we have a convergence, and in fact, they deduce the tightness result thanks to this convergence. And so we start here, our work with Nicolas and Gregory, and now the first thing to do, even if it's not the more complicated thing to do, is really to try to construct with these two processes our space S alpha. So to have a candidate for our scaling limit, because here we only have two processes and we need really a geometry. Okay? And to do that, we are going really to think in 2 times using 2 building blocks. First, the loop tree structure, and then the labels. And so for the loop structure, this is where we are going to take the alpha stable loop that was introduced by Nicolas Curin and Igor Konczynski. And this is just the loop tree induced by alpha stable excursion. And you can think about it as, okay, the CRT or the Brownian tree is encoded by a Brownian motion, and with the same kind of construction, you can use a alpha stable excursion to construct a loop tree. So the idea is really here. You have 2 simulations, so you have the alpha stable excursion, and every jump is a loop. And here I have drawn every jump with a color and the associated loop with the same color. So really you can think about it as you follow the contour of the loop tree, and when you see a loop, you have a jump. And you can recover the loop tree just using the excursion by gluing some points of the segment 0, 1. And so I will say that S and T are equivalent for X, for the Levy excursion, if they are the same point for the loop tree. Okay? So for example, the extremal points of a jump are the same points on the loop. And now that we have this interpretation in terms of continuous loop tree, in fact what happens is that the label process of Le Gall and Armand becomes very nice in some sense when you look it from the loop tree. In fact, it's just a Gaussian free field on it, or you can think about it just as a Brownian motion indexed by the loop tree. You have your label process, and when you see it, and here the colors of the loop tree are the labels. And when you see it in the loop tree, it's really just a Brownian motion. Okay. And this is, of course, very similar to what's happening for the Brownian sphere. For the Brownian sphere, the loop tree is the Aldous tree or the Brownian tree, and your Brownian labels are just Brownian labels. The difference is that in the case of the Brownian sphere, we can use all the technology and theory of the Brownian snake. And here we have to think again everything in some sense, and to find good ways to study this process. And really the first step was just to realize that that we can think about it in 2 times. First, the loop tree, that is just a alpha excursion, and so that we understand, and then putting the labels and using all the technology of Gaussian processes. Okay. So thanks to this to this perspective, we were able to prove some properties of this label process. And for example, we show that it's cyclically invariant. That's very important when you want to obtain some rerouting properties on your scaling limit. We also show that it has distinct local minimum. That's important when you are studying topology. And we have very strong controls of its module of continuity. That's good for estimates on volumes. And we have that this process is in some sense Markovian with respect to the loop tree. And what is important to keep in mind is not really in these four properties, is that you have some classical stochastic process, and every property of this process has a geometrical meaning in your scaling limit. Okay? So now that we have the analog of the loop tree, the label loop tree, and now I'm going to explain how we can construct from it a space, our space S alpha. So the construction now is really the same as the one of the Brownian sphere. So I'm going to give the definition, but it's not very, for this talk, it's not very important. What is important is really that we only use these two blocks of randomness, the loop tree and the labels. So we start just with this delta 0. St is just the label of S plus the label of T minus 2 times the maximum of the labels when you go from S to T or from T to S. The formula here is not important. What is important is that it's easy in terms of on the labels. And then now we define delta alpha as the biggest pseudo distance that is smaller than delta 0, and such that if 2 points are the same for the loop tree, then they are the same for delta alpha. And we will write that S and T are equivalent for delta alpha if delta St is equal to 0. So the exact definition is not important. It's just that we can recover it from our label continuous loop tree. And now I can define our limiting space. So S alpha is just the segment 0, 1 on this equivalent class with this distance. And this is just something is very similar to the construction, for example, of the Brownian tree or the loop tree or the Brownian sphere. It's really, we take the segment 0, 1, we make some identifications using a pseudo distance. And now what I'm going to use the rest of this talk giving some of the ideas, a general overview of the ideas that we use to prove that we actually converge to this object. But before that, I want to really to say that our construction is not something abstract. So the loop tree has a topological meaning. The faces, the loops are the faces of our scaling limit, and the labels have a geometrical meaning. In fact, what happens is that if you consider, so if you draw your loop tree like this, so the vertical axis is just the labels, you obtain that there is only one point, T stat, when you realize the minimum of the labels. That's something that depends only on the process. Okay? And what happens is that the distance to this T start for other T is just the difference of labels. So the labels are just saying you what are the distances to this T start. And that's the reason why we are going to take the root just T start. Okay, so it's really that the labels are saying you a distance to the root. Okay, I want also to mention that okay, we have the Lebesgue measure on 0, 1, and if you take the push forward measure by this equivalent class, you obtain a measure on the limiting space, which, and we show it, is the limit of the counting measure on vertices of a planar map. So really, we have a uniform measure on the limiting space, and the root is just a typical point for this measure. So what we have is a good measure and a point from which we understand the distances to it, and this point is just typical. And now I'm going to say a few things about the proof. And I want to start by saying a few words about the topology. And to be able to do that, I need first to explain what is more or less the general strategy to obtain scaling limits of planar maps, and why we have this strange definition in terms of the segment 0, 1 under some equivalent class, because it can be weird. So what we do is, okay, we want a convergence in Gromov-Hausdorff. But the Gromov-Hausdorff topology is very general, it's complicated, and so on. And so here I'm going to present a useful way to represent maps that is very useful to control the Gromov-Hausdorff topology. So the idea is just you start from your planar map. So let's say that you have n vertices, and you take your segment 0, 1. And then you put the first vertices at 0, the second one 1 over n, and so on and so on. Okay, so you have now your vertices on the segment 0, 1, and you introduce the pseudo distance. So when I say pseudo distance, is that you can have 0 between 2 points that are not the same. So that for every s and t, dnst is just the graph distance between ns and t. Of course, here I'm taking an interpolation to define it, but okay, let's say this. And what happens is that your planar map is almost the same thing as the segment 0, 1, where you glued together the points identified by dn. So the points that, such that dn is 0, and with the distance dn. And of course, this is reminiscent of our definition of the scaling limit as alpha. And now the nice thing is that the convergence for the Gromov-Hausdorff topology of Mn can be translated in terms of this dn, which is just a function from the square, unit square, to the positive, non-negative numbers. Okay, and so the convergence of Mn is just the convergence of this new distance, so the distance rescaled. Okay? And to understand the topology of Mn is just to understand what points are identified by dn, and then to understand the limiting topology is just to understand where the limit distance vanishes. Okay? And so this is quite similar of what Jacopo presented yesterday. So you have a permutation that's a complicated object, so you represent it as a measure on the square. And here we do more or less the same thing. It's complicated, a map is complicated, but we can see it just as some function on the square. Okay? But the nice thing is that here we are controlling the Gromov-Hausdorff convergence. Okay, so that being said, now I can see a few things about the proof. So the first thing is to use the tiniest result. So the idea is that we can take a subsequence such that this dn rescale converges to some random function on the square, d. And in fact, this function is continuous. And so we take a subsequence such that we have this convergence almost surely. And then our theorem is just to prove that d and delta alpha are the same. Okay? But well, this was, well, it's not so easy, at least for us. So what is easy to do is to use really the Bouttier-Di-Francesco encoding to see that you can take a coupling such that d is smaller than delta alpha, and such that you see exactly the same thing from the root, from T star. So this is really when you look at the Bouttier-Di-Francesco encoding, you obtain this. It's really, this is not difficult. Okay, so all the work now is to show the reverse inequality that delta alpha is smaller than d. Okay, but okay, it's not so bad because we see exactly the same thing from a typical point, and we know that delta alpha controls d. And so the first step to obtain our main result is to show that d and delta alpha defines the same topology, that in fact they vanish at the same points. And we show even more, so we show that d is, d vanishes only if delta alpha vanishes, but we show that this is only possible if s and t are the same for the loop tree, or if they are the same for delta 0 alpha. And delta 0, the definition is easy to write it in terms just of the labor process. And so in some sense, you can think about it as you only have points that are identified by the loop tree and points that are identified by the labor process in a very trivial way in some sense. And so again, you have these two blocks structure, your loop tree and your labor process. Okay? So maybe if I have time, I will say a few things about the proof. Okay, why not? So the idea, so I'm just going to give the idea because the proof, of course, is just using stochastic processes and so on, but the idea is a topological idea. So we start with our space as alpha, and we consider the cactus representation. So the cactus representation, let's say something like this. Well, it's not very good. Okay. So the cactus representation is just that we take the root, O star or T star, what you prefer, and we represent each point by its distance to the root. So here you have, let's say, delta alpha O star. Okay. So you obtain something like this. And now, as we know that D is smaller than delta, we can see that we can define D on S. We can see it as a pseudo distance on S. And now the game is to show that two different points of S cannot be identified by D. Or, in an equivalent way to say it, is that D is a distance on S. Okay? That really you are not gluing anything. Okay, I'm going to take colors. Okay. So let's see what's happening. Imagine that you want to glue, I don't know, this point and this point. Okay? So they are at different levels. So the distances to the root are different. But as we know that we see exactly the same thing from the root, so we know that okay, the distance for D to the root are the same. And so we cannot glue together these 2 points because D is a pseudo distance. Okay? It's not possible thanks to the fact that, I'm going to write it here, so it's not possible because we have this. Okay, so if you want to identify 2 points, you need to identify 2 points which are at the same level, okay? At the same distance to the root. Okay. But now we are dealing with geodesic space. So if you are identifying 2 points, it means that you have some path connecting them such that I don't know, let's say gamma, such that the length for D of gamma is 0. So you are identifying all the points of this path. Okay. But now imagine that your path is making a vertical movement. Then, again, you are identifying 2 points which are at different levels of on your cactus representation, so it's not possible. So if you want really to, okay, that's not very good. So if you want really to glue together two different points, you have to do it using a path staying at the same level. Okay. And what happened now is that we have a topological constraint. What we show is that for every point, we have, at the left and on the right, we have faces that cut this level. And so now, if you want to go from, you cannot do that, you cannot cross the face. So because, okay, it's a hole, so if you want to go from this point to that point, you need to contour one of the faces, and so you need to perform a vertical movement. And so it's not possible. So really the idea is that the faces, the faces are helping you, and really they introduce some constraints on your topology that there is not the case for the Brownian sphere because you have the topology of the sphere. Okay, so really is that idea that you have to contour some faces to go from one point to the other. I'm not going to say how we show that this is equivalent to be in the same point for the loop 3 or for delta 0, but this is the idea, and of course the proof is stochastic processes. Okay. Yes.
How different is this theorem when you prove from the case of the Brownian map?
Okay, so in the Brownian map, you don't have this. Maybe you can use like some slides as faces, but the problem is really that you cannot use this kind of argument. You really have to. I don't have in mind the proof, but the Gall's proof. But okay, he considered like a variant of the Brownian sphere, which cutting it by following the geodesic between a typical point and the root. And
is it fair to say that the conclusion is the same, but the argument is different? That
yes.
The conclusion is that you cannot indicate it without the next one?
No, you have the same result. In fact, for the Brownian sphere, you have the same statement. You identify only points that are the same for the Brownian tree, or points that are the same for delta 0 for yes, but the proof, the idea of the proof is, in fact, this proof is easier, is a lot easier than in the case of the Brownian sphere, because you don't have to have, in some sense, a uniform control of horizontal movement. Here, you only need to show that you have really faces cutting each level. And this is just an argument using René-Wald theory, and but it's not the difficult part of. So, if you want, the moral of the idea is that in the Brownian sphere case, everything is explicit, and you have the Brownian snake to work with it, and so you can really make exact computations and so on. Here we don't have really exact computations, but we have the faces which introduce some constraints. And for example, I don't know if you take like the same construction but using a loop tree with a Brownian part, okay, which is a mixture between a loop tree and a Brownian tree, then I don't know at all how we can prove it, because you cannot any longer have you don't have the faces really they don't do that, and you don't have any more explicit computation. So really, there's something different there. Okay. Where is the? Okay. So how time I have left? So now that we have that we know what is more or less our topology, I'm going to say how we can study it, because this is a characterization, but it does not say almost anything about it. And okay, the idea is to use that we have this two-block representation, the loop tree and the labels. And now the game, as usual, is to find a good representation of these two equivalent classes, so the class of the loop tree and the one of delta 0. So the idea is to use a lamination of the disks. So what we do is just we take the segment 0, 1 and we glue together the two extremal points in order to obtain a circle. And then 2 points that are the same for one of the equivalent class, we draw a hyperbolic arc between them. And we obtain these two lamination of the disks. Okay, and the good news is that the lamination induced by the loop tree is exactly the alpha stable lamination studied by Igor Konczynski, and so we know a lot of things about it. And the one induced by delta 0 is not a canonical one, but what is not difficult to prove is that we only have triangles. Okay? Or every face is a triangle, and then from a topological perspective, it's easy to study. It's not very hard. And now what we have to do is to understand both equivalent classes at the same time. And the idea is just, okay, we take the circle and we glue it together in order to obtain a sphere. So here is a simulation. So here in the north hemisphere, we have the lamination of delta 0, and on the south hemisphere, we have the lamination of the loop tree. And so now what we have to understand is the equator and what points are connected by a blue or red arc. Okay, and this is just a representation again. It is very useful. And Le Gall and Paulin use the same kind of techniques to study the topology of the Brownian sphere. Okay? And what we show is using this representation, we show that if you fill in all the faces of the loop tree, so you fill every face with a disk, then using Moore's theorem, so some classical theorem of topology, that we have the topology of the sphere. And that means that we can embed our space in a continuous way on the sphere. And we use also this representation to show that we have the topology of the serpentine carpet when alpha is bigger than 3/2. Okay. And now I have, well, why not? So I'm not going to be able to finish this part, but so this is what's happening for the topology, for a topological perspective. And now I'm going to say just a few words about geodesics, and more or less the idea that to prove that really we have D equals delta alpha, or that we converge to S alpha. And the idea is again to come back to the discrete, so to the Boutier-Di-Francesco encoding, and to observe that we have a very special type of geodesics. In fact, if you take a white vertex with label A, and then you follow the contour, and your Boutier-Di-Francesco guitar encoding is creating a red edge, so an edge of the map between this guy and the next white vertex with label I-1. And if you continue performing this operation, you will finish in the point with the smallest label. Okay? And you obtain, in fact, in that way, a geodesic between your point and the point with the smallest label. And in the continuous, we have exactly the same thing. If you follow the running infimum, meaning that if you follow the new infimum that you see, then you are constructing geodesics to the root. So I'm going to finish with maybe this picture over here. So again, we represent the loop tree by the labels. And then if you take a point, then you just follow the running infimum until you hit the point with the smallest label, and you obtain a geodesic in your limiting space. So you have your stochastic process, you study the running infimums, and you obtain geodesics. And this is the same picture as for the Brownian sphere. You also have this kind of geodesics that we call simple geodesics. And what we show is that all the geodesics to a root are simple geodesics. And now I'm going to say a few things that are different from what's happening for the Brownian sphere. So, okay, if you take a leaf, so a point, if you remove it, you only have one connect component, then you have only one geodesic to the root. Okay. If you take a point which is a pinch point, which is between two loops, then you have two possible geodesics, two possible ways of running your infimum, because, well, when you follow your contour, you see it one time, then you see the loop on top of it, and then you see it a second time when you leave it. And so you have really two geodesics, like in this picture. And all the geodesics, you have this coalescence property as for the Brownian sphere. Okay. And these are the only two possibilities. You cannot have three simple geodesics to the root. And that was the case for the Brownian sphere, as Timothy recalled. Okay. And this is maybe the most important thing for us, is that the simple geodesics always, for every alpha, hit the faces. Hit the faces meaning that really there are bonding between the faces. And this is really very helpful when we study the metric. But okay. I will stop here, but really that's a very important thing, to prove that we have this property that we are bonding in faces. And just to say a few things, in fact, we use that to create traps for the geodesics and to have metric constraints. And so really the proof then is to use this property with the planarity of our scaling limit to be able to recover the distance d just using delta alpha and the topology. Okay. Up. So I'm going to stop here. So thank you very much.
Questions?
Okay, so you did not say how you prove that d is indeed equal to delta. You
Sorry?
said that d is equal to 0 and only delta is equal to 0, but how do you prove the equality?
The equality for the rest of the... Okay, okay, so the goal is really to prove this. And the idea is, as for the Brownian sphere, the idea is that you are going to, so now you can work on the topology of S because you know that D is a distance on it. And the idea really is now to, we know that we see exactly the same thing when you go to the root. And okay, so the idea is really to take two uniform points. Well, they are not like this, but it doesn't matter. And if you take a D geodesic, that this D geodesic can be approximated just using simple geodesics. And the idea to do that is, so we don't have the Brownian snake anymore, so we cannot understand very well what is happening at a running infimum, and so we cannot really use the same kind of technique, but what happened is that the tessellation bijection of Gregory-Mirmont works also for this kind of maps, and so we can understand what is the typical landscape from a typical point of a geodesic. And what's happening is that if you take one point like this, so it's the picture here, okay? So imagine that you have your point ρ1 and ρ2. So from this point, so if you make a zoom like this, so imagine that you have gamma t here. Then your geodesic is not like this. If it's doing something like, you will have two faces like this, such that your geodesic is going from one to the other, and from the other, like this. Imagine here you have both 1 and 2. And then your root is something, for example, it's here. And what happens is that if you consider now a geodesic for going to the root, then the geodesic has to, from this point to the root, it has to cross this barrier here, this topological barrier, because you are bonding from one face to the other. So we're going to do something like this. And what happens is that we know that between two typical points, there is only one geodesic. So this simple geodesic is really staying, is intersecting the geodesic between ρ1 and ρ2, is the drawing that I put here. So if you are a gamma t and you want to leave, imagine that you want to leave from the left, then as you only have one geodesic between ρ1 and ρ2, then your red path has to be the same as the green one for some amount of time. And we can do this for all the points in this zone, and then you obtain really that some portion of your geodesic between two typical points is equal to the one. And then you have to control the other dimension of the points that are not like this, but this is not so hard, but it's again we use again the faces and the planarity again.
Okay, other questions?
Okay. Following on your question, so I understand correctly, you are using the unicity of geodesics between
yes.
the typical points. So would it give you a different proof for the Brownian map then, the same argument, or is there?
Okay, so for the Brownian map, you can use, you have a legal argument to show that there is only one geodesic, and you have a Gregory-Mirmont argument, and Gregory-Mirmont used this bijection with not to the root, but you have two roots and you have some delays. And this bijection works also for more general maps, and it works in our framework. And we use this construction to show that we have only one geodesic between two typical points. So is more or less the same, more or less the same as the one of Gregory proof of the. The difference, if you want, the big difference is that in the proof of the unicity of the Brownian sphere, you need to understand not only geodesics between 2 points, but also a star geodesics between 3 points. And here you don't have to do it any longer because you have the phases. And that's a very good thing because, okay, we have the same kind of ejection, but the object that we use, the loop tree, is more complicated than Brownian tree. And so things are more technical, and it's a good news that we don't need a bijection with 3 points. That's really that the phases are helping you.
Could you say a bit more about the threshold? Why 3/2? What happens when you are below 3/2?
Yes, well, I say that it's a phase transition because if alpha is bigger than 3/2, then the phases are just simple loops. And then we know that the topology is deterministic, is the one of the serpentine carpet. But for alpha smaller than 3/2, the phases are self-intersecting, and we don't know even the topology of a phase. So there is a difference, a huge difference there. And in fact, you have when alpha is smaller than 3/2, you have things like this. You have your phase is doing things like this. So you have things even stronger. So you have really zones that are disconnected just by 1 point from the rest. So your phase is here. So for example, one main difference is that for the Brownian sphere or for alpha is bigger than 3/2, you cannot have, you don't have pinch points that are disconnecting two region of the limiting space. Here you have really points that if you remove it, you obtain 2 connected components. And your topology is completely different. But the proof is more or less the same because, maybe in the dense phase, we could prove that we have something stronger than this. We have maybe that a geodesic going from here to here has really to pass from a fixed point and not like a windows like this. But the proof is more or less the same.
Okay. Are we finished? Okay, so thank you again, Armand.